Consider the following 1964 IMO problem number 2. Here is a view of this problem. ABC are the sides of a triangle, and without loss of generality, let's assume that A is the largest of the three, followed by B, followed by C. And we can do this because it seems our inequality is just symmetric, and so that will be useful. We want to prove this inequality. Well, the key move is to make sense of these and how they relate in this inequality. And a crucial idea is just the following: is just to split this a squared into two pieces. So therefore, if and only if, consider this inequality instead. So it's not trivial, I admit that. It's quite a surprising fact, but so you can just write it like this, and you might wonder why would we do such a thing at first, but I'll just explain in a minute. C times A plus B minus C, so that's what we want to prove. And check this out. So if you compare this term with this term and then that term, it turns out that, so I have the following claim. So I claim that, well, given this inequalities, so A times B plus C minus A is less than or equal to B times C plus A minus B, which is further less than or equal to C times A plus B minus C. So let me go ahead and prove this claim first, and then we'll come back to our original inequality. So obviously, because all three parts are symmetric, we can just prove one of the inequalities and the other one will follow directly. This one will just follow directly. So let's focus our attention on the first one. So we can connect it with if and only if statements. So if and only if, so we can just expand basically. A times B plus A times C minus A squared is less than or equal to something we still need to prove. B times C plus A times B minus B squared. It is clear that the AB terms cancel, and I'll go ahead and move everything on the left hand side to the right hand side. So again, we have an if and only if statement. 0 is less than or equal to, so we have A squared minus B squared, and then we also have, well, minus AC plus B times C. And we can now combine these. Well, obviously this is just A minus B times A plus B, this one, and then we can have minus, we can factor out the C here. If you factor out the C, we have A minus B, yes. And finally, another if and only if statement. 0 is less than or equal to, we further factor out the A minus B terms. We would get this following inequality that we need to prove. But this is obvious. The reason being that, well, obviously this is greater than or equal to 0. Remember our initial assumption. And further, this is greater than or equal to 0. Why would that be? Well, this follows from the fact that A, B, and C are the sides of a triangle, and this follows directly by the triangle inequality, of course. By the triangle inequality, that holds true. So therefore, this statement is true, which implies this is true, this is true, and finally our claim is true. So what that tells us is the following. We have, now you guys are seeing where I'm going. So we have I want to compare these two sequences. So we have two sequences. They are ordered sequences. So for instance, this one is a decreasing sequence. This one is an increasing sequence. And if I combine them in a special way, I can make use of the rearrangement inequality, something we used in 1978 IMO problem number 5 and 1975 number 1, I guess. And this is the third time we are using this inequality. That won't be the last time. I'll solve a few more IMO questions using this useful rearrangement inequality. But we can combine them now. But obviously we have an eye on the desired result. So looking into this, we just realize that we're not surprised to see that this will be less than or equal to basically anything, right? Why? Because we are combining in our two sequences the largest one of one sequence. Oops, hold on a second. So let's go back. Okay, oops. Maybe, the largest one of this sequence, we are combining it with the smallest one of the second sequence. Do you see that? So so this is like a sequence x sub I, and this is a sequence of y sub i's. So the smallest element, we are combining it with the largest element here, and we add, then we combine this one and that one, and finally combine. When I say combine, I mean multiply this one and that one, and we calculate the sum product. That's exactly the left hand side of our inequality, desired inequality. But by the rearrangement inequality, this would be less than or equal to any permutation of say one of the sequences. We can fix the second sequence, if you will, and we can permute the elements of the first sequence and recalculate sum products. All these sum products would be larger than or equal to that absolute minimum by the rearrangement inequality. So therefore, let's write down what we have so far. So far we know that we have two sequences, namely sequence CBA, and then the second sequence, and this time I kind of aligned them, if you will. B plus C minus A is less than or equal to B times A plus C minus B, which is less than or equal to C times A plus B minus C. Now let's get to business by rearrangement inequality. So I will apply rearrangement inequality twice. So firstly, like I said, so we multiply the largest with the smallest on the other sequence. So we would get A square times B plus C minus A, plus, and then the middle one with that middle one, B square times A plus C minus B, and then finally C square times A plus B minus C. Now this thing is definitely less than or equal to, so we can make any permutation of this sequence. So let's start with BCA first. So I'll multiply the smallest one with B first. So I would get AB times B plus C minus A. Maybe I should write it the other way around. B times, so this is our second term. This term, the smallest term, and then this is the middle term, right? And then I'll multiply this middle term with the smaller term here, so plus C times A plus C minus B, and finally we have one more term. The largest one here will be multiplied with this largest one, plus A times C A plus B minus C. And I'll do it again. So I will apply rearrangement inequality once, and then I'm applying it the second time. The left hand side won't change, so we still have A squared times B plus C minus A, plus B squared times A plus C minus B, plus C squared times A plus B minus C. And that's again less than or equal to, this time the smallest element here I will multiply with C, so C times A, and again by the rearrangement inequality, that's correct result. A times B, A plus C minus B, and finally B times plus B times C A plus B minus C. And that's it. We will just go ahead and add both sides of this whole thing, these two inequalities. So we just add them, Well, the left-hand side will obviously be twice the left-hand side of the desired result. So 2 times that. So let's just write that down. So we have 2 times, well, A squared, B plus C minus A. Well, as you can imagine, algebra problems are always bashy. So, what can you do, huh? A plus B minus C less than or equal to, okay, so the right hand side is important. So let's get a different marker, and hopefully things should cancel here. So we have Oh gosh, this is really bad. So we have, if you want, let's count the ABCs first. We have one ABC here, and then we have CB here, another ABC, that's 2 ABC, and then ACB, 3 ABC. We have CAB, 4 ABC, ABC, 5 ABC, BCA, 6 ABC. So we have 6 times ABC. Alright, so what else do we have? So let's have these terms. B square A here. Do we have any other B square A term here? Not here. So we have a B square A term. Let's write that down for now. So as a result, plus we have a C square B term. C square B term. We have an A square C term. A square C. And then we have C square A term again. C square A, I mean the first time, A square B term, A square B term, and then B square C term, B square C. I think we are done with those. And finally I have minus A, oh gosh. Okay, that's good. Minus, okay, A square B, okay, that's good. Minus A square B, and then I have minus B square C, minus B square C, minus C square A, minus C square A, minus A square C, minus A square C, minus B square A, and finally minus C square B, minus C square B. Now we can obviously see that things are cancelling here. So we have minus A square B, they are gone. Minus B square C, they are gone. Minus C square A, they are gone. Minus A square C plus A square C, minus B square A plus B square A, minus C square B plus C square B, they are all gone. We have on the right hand side 6 ABC left. We have a 2 here. We can divide both sides by 2, and we get the desired. Divide both sides of inequality by 2, and we get the desired inequality, which is obviously the left hand side without the 2, and then 3 ABC on the right hand side. And this was exactly what we wanted to show, and we're done.